Hello and welcome to Physics Before Bed. If you enjoy calm journeys through the mysteries of the universe, please take a moment to like the video and subscribe to the channel. It really helps more curious minds find these quiet explorations of science. And before we begin, I'd love to know where in the world you're watching or listening from tonight. Maybe you're near the ocean, where the tides are already part of daily life. Or perhaps you're far inland, where the rise and fall of the sea happens quietly beyond the horizon. Wherever you are, the story we're about to explore is unfolding there too, because the tides are part of a global rhythm that touches the entire planet. Tonight, we're going to follow one of the most gentle and persistent forces in nature. Every day, across thousands of kilometers of coastline, the ocean slowly advances and retreats. Harbors fill and empty, beaches appear and disappear. Estuaries breathe in and out as water rises and falls with a quiet patience that has repeated for billions of years. If you've ever stood beside the sea long enough, you've probably noticed this slow transformation. Rocks that were dry a few hours earlier become submerged. Boats lift softly with the rising water. The shoreline shifts, almost imperceptibly at first, until the entire landscape seems to change. And yet the ocean itself isn't choosing to move. It's responding. Far above the waves, nearly 400,000 kilometers away, the moon is exerting a gravitational pull on our planet. Invisible and silent, this pull stretches across space and reaches down into the oceans of Earth. Not with sudden force, but with a gentle tug that shifts entire bodies of water across the surface of the world. In a sense, every tide is part of a conversation between Earth and the moon. It's a conversation written in gravity. For centuries, humans tried to understand why the sea behaved this way. Ancient observers noticed the pattern long before modern science existed. Some suspected a connection with the moon, watching carefully as the tides rose higher, during full moons and new moons. Others proposed strange explanations involving winds, hidden currents, or even breathing oceans. Eventually, through the work of astronomers, mathematicians, and oceanographers, the deeper truth began to emerge. The tides are not random movements of water. They are the visible expression of celestial mechanics, the physics that governs how massive bodies move through space and influence one another. And once we begin to look closely, the story becomes even more fascinating. Because the tides are not just about the moon pulling on Earth's oceans. They reveal something far bigger, a delicate gravitational dance between Earth, the moon, and the sun. A dance that slowly reshapes our planet over immense spans of time. The tides are gradually slowing Earth's rotation. They are gently pushing the moon farther away from us each year. They are even stirring the deep ocean currents that help regulate Earth's climate. In other words, the tides are part of the long-term evolution of our planet. But the beauty of this story is that it begins somewhere very simple. A shoreline, a rising tide, and a distant moon hanging quietly in the sky. Tonight, as we explore how the moon controls the tides, we'll follow that quiet gravitational influence from the scale of the shoreline all the way out into the vast mechanics of the cosmos. We'll look at how gravity stretches the oceans, why tides rise twice each day, how the sun subtly strengthens or weakens them, and how the shapes of the continents guide the movement of water around the world. Along the way, we'll also discover something surprising. The same tidal forces that move Earth's oceans are shaping other worlds across the solar system. On distant moons, tides can melt ice, drive volcanoes, and perhaps even create environments where life could exist. But it all begins here, with a calm ocean, a distant moon, and a quiet pull that never stops. So settle in, relax, and let the rhythm of the tides carry us gently into tonight's exploration of how the moon controls the oceans of Earth. If you stand beside the ocean long enough, something remarkable begins to reveal itself. At first, the shoreline seems almost still. Waves roll in and retreat, seabirds wander along the sand, and the horizon remains steady in the distance. But give it a little time, perhaps an hour or two, and the entire scene slowly begins to transform. Rocks that were once dry become surrounded by water. A stretch of beach that seemed wide and open gradually narrows as the sea creeps inland. Boats resting quietly in a harbour begin to lift higher against their moorings. Nothing dramatic is happening. There is no sudden surge or violent motion. Instead, the ocean is rising with a calm patience that is almost easy to miss. This slow movement is part of one of the most reliable rhythms on Earth. It is the tide. Every day, across nearly every coastline on our planet, the oceans rise and fall in a repeating cycle that has continued for billions of years. Harbours fill and empty. Estuaries breathe in and out like enormous lungs. Entire coastal ecosystems adapt their lives to the steady advance and retreat of seawater. And yet, the ocean is not moving randomly. It is responding to forces that extend far beyond the shoreline. The tides are the visible result of gravity acting across an entire planet. In particular, they are shaped primarily by the gravitational influence of the Moon. Although the Moon hangs quietly in the sky, its presence is anything but passive. Its gravity reaches across the vast distance between the two worlds and gently pulls on Earth. Not just on mountains or forests or cities, but on every part of the planet at once. The oceans, however, respond more visibly than anything else. Water flows, it shifts, it redistributes itself across the globe when forces act upon it. Because of this mobility, the oceans become the most obvious place where the Moon's gravity reveals its influence. To understand how extraordinary this really is, it helps to consider the scale of what is happening. Earth's oceans contain roughly 1.3 billion cubic kilometers of water. Spread across more than 70% of the planet's surface, they form a vast, continuous body of fluid that wraps around continents and stretches across thousands of kilometers. And yet this enormous mass of water is being gently shifted by an object floating far away in space. The Moon orbits Earth at an average distance of about 384,000 kilometers. That is roughly 30 times the diameter of our planet. Despite this immense separation, gravity never truly fades away. It grows weaker with distance, but it never disappears. The gravitational attraction between two objects depends on three essential ingredients: their masses, the distance between them, and the fundamental law described by the 17th century physicist Isaac Newton. Newton showed that the strength of gravitational attraction could be expressed with a simple relationship. In words, the idea can be summarized as follows. The gravitational force between two objects equals the gravitational constant multiplied by the mass of the first object multiplied by the mass of the second object, divided by the square of the distance between their centers. This principle, known as the law of universal gravitation, revealed something profound. The same force that causes an apple to fall from a tree also governs the motion of planets, moons, and stars. In the case of Earth and the Moon, their mutual gravity binds them together in an orbital partnership that has lasted for more than 4 billion years, and within that partnership the oceans respond. But the story of tides is not simply about a distant body tugging on Earth's water. The physics involved is more subtle and far more fascinating. Gravity does not pull equally on every part of Earth. The side of our planet that faces the Moon experiences a slightly stronger gravitational pull than the centre of the planet. Meanwhile, the far side of Earth experiences a slightly weaker pull. These tiny differences in gravitational strength create what scientists call tidal forces. Tidal forces stretch the Earth very slightly along the line pointing toward the Moon. The planet itself flexes almost imperceptibly. The crust rises and falls by a few centimeters. Even the atmosphere experiences gentle tidal motions. But the oceans, once again, show the effect most clearly. Water shifts. It gathers into enormous bulges that slowly move around the planet as Earth rotates beneath them. As coastlines pass through these bulges, sea levels rise and fall, creating the familiar rhythm of high tide and low tide. Seen from space, this motion would look less like waves and more like a slow breathing of the planet's oceans. For a long time, scientists wondered just how much energy this process involved. After all, moving such vast quantities of water must require enormous forces. In the 20th century, one of the researchers who explored this question in detail was the American oceanographer Walter Munk. Walter Munk spent decades studying the dynamics of the global ocean. Working with colleagues at institutions such as the Scripps Institution of Oceanography, he investigated how tidal motion distributes energy across the planet's seas. Munk discovered that tides do far more than simply raise and lower the water along coastlines. They generate powerful currents that flow through deep ocean passages. They stir layers of water that would otherwise remain separate. They help drive mixing processes that influence ocean circulation and even climate patterns. In other words, tides are not merely a coastal curiosity. They are part of the engine that keeps the oceans moving. Without tidal energy, the structure of Earth's oceans would be very different. Deep waters might remain isolated for far longer periods. Nutrient circulation would change. The entire marine environment could behave in unfamiliar ways. All of this begins with a gravitational interaction between two celestial bodies, Earth and the Moon. Which brings us to the central mystery at the heart of this story. How can an object that seems so distant, and often so small in the night sky, exert enough influence to shift the oceans of an entire planet? The answer lies in a combination of gravity, motion, and the remarkable responsiveness of fluid systems. Understanding it will require us to look more closely at the partnership between Earth message delivery timed out. Please try again. Retry long before satellites measured the height of the oceans, and long before mathematical models predicted the motion of tides years into the future. People living beside the sea were already aware that the ocean moved with a steady and reliable rhythm. If you spend enough time near the shoreline, the pattern becomes impossible to miss. Harbours fill slowly and then empty again. Fishing boats that were floating comfortably a few hours earlier may end up resting gently on mud or sand as the water retreats. Rocky outcrops appear and disappear in a quiet cycle that repeats day after day. For coastal communities, this rhythm was not an abstract scientific curiosity. It was something practical and immediate. The tide determined when ships could safely enter shallow ports. It influenced when fishermen launched their boats. It shaped when shellfish could be gathered from tidal flats. In many places, entire daily routines quietly adapted themselves to the movement of the sea. What makes this especially remarkable is that these observations emerged thousands of years before anyone understood the physics behind them. Ancient sailors did not possess telescopes or modern astronomical instruments. They had only careful observation, long experience, and a deep familiarity with the sea. Over time, they noticed that the tides did not occur randomly. Instead, they followed a repeating pattern that seemed connected to the moon. In many coastal regions, people noticed that tides became particularly strong during the full moon and the new moon. During these times, the ocean rose higher than usual and fell lower than usual. Even without modern science, the connection was difficult to ignore. The changing position of the moon in the sky appeared to be linked somehow to the movement of the ocean. One of the earliest thinkers known to propose a direct connection between the moon and the tides was an ancient astronomer named Seleucus of Seleucia. Seleucus lived during the 2nd century before the Common Era in a region that is now part of modern Iraq. He was a supporter of the heliocentric idea that the Earth moves around the Sun, a view that was quite bold in his time. Seleucus is remembered not only for supporting that idea, but also for suggesting that the tides were caused by the moon. This was an extraordinary insight. Without any knowledge of gravitational physics, he reasoned that the moon must somehow influence the oceans of Earth. Unfortunately, very little of Seleucus's original writing survives today. Most of what we know about his ideas comes from later historians and philosophers who recorded fragments of his work. Even so, the fact that he recognized a connection between the moon and the tides stands as one of the earliest examples of scientific reasoning applied to ocean behavior. As centuries passed, interest in the heavens and the oceans continued to grow in many parts of the world. In the medieval Islamic world, astronomy became a highly developed scientific discipline. One of the notable figures during this period was Ibn Yunus, an Egyptian astronomer who lived around the late 10th and early 11th centuries. Ibn Yunus carried out extremely precise observations of the moon's motion across the sky. Using large observational instruments and careful records, he compiled detailed tables describing the position of the moon at different times. His work significantly improved the accuracy of lunar astronomy. Although Ibn Yunus did not directly solve the mystery of tides, his observations played an important role in improving humanity's understanding of how the moon moves around the Earth. And since the motion of the moon is deeply connected to tidal behavior, more accurate knowledge of lunar motion eventually made better tidal prediction possible. These early efforts show something important about the development of science. Understanding complex natural phenomena rarely happens all at once. Instead, it usually unfolds through many generations of careful observation, measurement, and refinement. By the time Europe entered the age of global exploration, tides had become an important practical concern for navigation. Ships travelling between continents needed reliable knowledge of when water levels would rise and fall in coastal ports. A ship entering a harbour at the wrong time could easily run aground. This practical challenge led scientists and navigators to begin studying tides in a more systematic way. One of the key figures in this effort was William Whewell, a 19th century British scientist whose interests ranged across mathematics, philosophy, and natural science. Whewell was fascinated by tides and believed that understanding them required global observation rather than isolated local measurements. During the 1830s, Whewell began collecting tidal data from ports around the world. Working with naval officers and scientific observers, he gathered measurements of when tides occurred and how high the water rose at different locations. From this growing collection of data, Whewell produced some of the earliest global tidal charts. These maps showed lines connecting places where high tide occurred at the same time. The lines were known as cotidal lines, and they revealed that tidal motion was not simply a uniform rise and fall across the oceans. Instead, the tides moved in large, sweeping patterns across ocean basins. This discovery was a major step forward. It showed that tides behave like enormous waves travelling across the surface of the ocean, guided by the shapes of continents and the depths of ocean basins. The oceans were not simply rising and falling in place. They were part of a complex moving system influenced by both gravity and geography. Whewell's work represented an important moment in the history of tidal science because it combined several different areas of knowledge. Navigation provided the motivation. Astronomy helped explain the influence of the moon, and careful coastal observation supplied the data needed to reveal global patterns. In other words, the science of tides emerged from the meeting point of sailors, astronomers, mathematicians, and natural philosophers. Even today, tidal research continues to rely on this combination of disciplines. Modern oceanographers use satellite measurements, mathematical models, and centuries of observational data to understand how tidal forces move water around the planet. But the foundations of that understanding were laid by generations of observers who simply watched the sea and noticed its rhythm. The shoreline provided the clues, the moon provided the mystery. And patient human curiosity slowly began to connect the two. By the time scientists finally uncovered the true physical explanation of tides, the groundwork had already been prepared by centuries of careful observation. The ocean had been revealing its rhythm all along. Humans just needed time to learn how to listen. When people picture Earth from space, they often imagine the familiar blue marble floating quietly against the darkness. Swirls of white cloud drift across continents. Vast stretches of deep blue ocean dominate the view. From that distance, the planet looks calm and still. But this appearance hides a more dynamic reality. Earth is not a rigid object sitting motionless in space. It is a rotating world wrapped in a vast layer of moving water. Oceans cover roughly 70% of the planet's surface, forming an interconnected global system that flows around continents and across enormous basins. In many places, the ocean reaches depths of several kilometers. The average depth of the global ocean is a little under 4 kilometers, which means the oceans contain an extraordinary volume of water. This immense body of water behaves like a fluid shell surrounding a rotating sphere. Unlike solid rock, water can move easily in response to forces acting upon it. If gravity pulls slightly more strongly in one region, the water can slowly shift in that direction. If wind pushes across the surface, waves form and currents begin to flow. If temperature differences appear between regions, large-scale circulation patterns develop that can transport heat across entire oceans. Because of this flexibility, the oceans are constantly responding to influences both from within Earth and from outside it. In the context of tides, the key idea is simple but powerful. The oceans can move. When gravitational forces from the moon and the sun act on the planet, water does not remain perfectly fixed in place. Instead, it redistributes itself slightly across the surface of the globe. The result of this redistribution is what we observe as tides. To understand why this happens, it helps to think about the oceans not as separate bodies of water, but as one continuous fluid system. Although we give names to different regions such as the Atlantic Ocean, the Pacific Ocean, and the Indian Ocean, all of these waters are connected through narrow passages and deep basins. Water can flow between them, and gravitational forces act on the entire system at once. Imagine a thin layer of liquid coating a slowly spinning ball. If that ball experiences a small gravitational pull from one direction, the liquid layer will shift slightly. It will stretch and redistribute itself until the forces acting on it reach a new balance. That is essentially what happens on Earth, though on a vastly larger scale. Our planet rotates once roughly every 24 hours. As it spins, the oceans move with it. At the same time, the Moon exerts a gravitational pull that is slightly stronger on the side of Earth facing the Moon and slightly weaker on the far side. Because water can move relatively freely, the ocean responds to these differences in gravitational force. This flexibility is one of the reasons the oceans provide such a clear and visible expression of tidal motion. But it is important to recognize that water is not the only part of Earth responding to these gravitational influences. Even the solid portions of the planet experience tidal effects. At first this might seem surprising. Rock feels rigid and unchanging beneath our feet. Mountains and continents appear stable over human timescales, yet when measured carefully with modern instruments, the Earth's crust is not completely immovable. Under the influence of gravitational forces from the Moon and the Sun, the solid body of Earth actually flexes slightly. These subtle movements are known as solid Earth tides. Instead of water rising and falling along coastlines, the entire surface of the planet deforms very slightly. The crust bulges outward in certain regions and contracts in others. The vertical motion involved is usually only a few tens of centimeters, far smaller than many ocean tides, but still measurable with precise instruments. This phenomenon reveals an important truth about our planet. Earth is not perfectly rigid. Over large scales and long periods of time, the rocks that form the crust and upper mantle behave in a somewhat elastic way. They can stretch and compress slightly under gravitational stress. Scientists began to understand this behavior more clearly through the development of geophysics during the 19th and 20th centuries. Careful measurements of Earth's shape and gravitational field revealed that the planet responds dynamically to external forces. One of the researchers who helped advance the mathematical understanding of tides was the British scientist Joseph Proudman. Joseph Proudman was an oceanographer and mathematician who worked during the early 20th century. His research focused on applying mathematical physics to the behavior of tides and ocean circulation. Proudman recognized that tides could be described using equations that account for gravity, Earth's rotation, and the movement of fluids across the curved surface of the planet. His work contributed to the development of what is now called physical oceanography, a scientific field that studies how physical forces shape ocean behavior. Proudman's research showed that tides are not simply the ocean rising and falling like water in a bathtub. Instead, tidal motion behaves more like a vast system of waves traveling through ocean basins. These waves are influenced by the rotation of Earth, the shape of the seafloor, and the positions of continents. Mathematically describing this motion requires combining several physical principles. Gravity pulls on the oceans. Earth's rotation introduces what is known as the Coriolis effect, which deflects moving water to one side in each hemisphere. And the geometry of ocean basins shapes the paths along which tidal waves can travel. By analysing these interactions, scientists like Proudman helped transform tidal science from simple observation into a predictive discipline. Yet even with these advances, one fundamental insight remains central. Tides are not confined to the oceans alone. They are a planetary phenomenon. The Moon's gravitational pull stretches the entire Earth very slightly along the line connecting the two bodies. The oceans respond visibly because water can flow easily, but the underlying planet is also participating in this slow gravitational dance. In fact, modern instruments such as laser ranging systems and satellite measurements can detect these subtle deformations with remarkable precision. The Earth's surface rises and falls gently as the Moon passes overhead, almost as if the planet itself were breathing. This realization offers a different perspective on our world. Instead of imagining Earth as a solid object surrounded by moving water, it may be more accurate to think of the entire planet as part of a flexible system responding to gravitational forces from space. The oceans shift most visibly. The crust flexes quietly beneath them. Even the atmosphere experiences small tidal motions driven by solar heating and gravitational influences. All of these responses are connected. They remind us that Earth is not isolated from the rest of the universe. The planet participates continuously in a network of gravitational relationships that extend far beyond its surface. Every rising tide along a coastline reflects this deeper interaction. It is the visible ripple of a force that reaches across hundreds of thousands of kilometers, gently reshaping the oceans and, in subtle ways, the entire planet itself. If the tides are the visible motion of the oceans, then the quiet driver behind much of that motion is a familiar object that rises in the night sky. The Moon appears small and distant when seen from Earth, but in physical terms it is a surprisingly substantial companion. The Moon's diameter is a little over 3,400 kilometers, which makes it roughly 1/4 the width of Earth. Its mass is about 1/81st of Earth's mass. That may sound small at first, yet in the context of planetary satellites it is unusually large compared with the planet it orbits. Many moons in our solar system are tiny fragments compared with their parent planets. The Moon is different. It is large enough that the Earth and the Moon influence each other strongly through gravity. In fact, some astronomers occasionally describe them as a kind of double system, rather than a simple planet with a small satellite. Distance also matters when it comes to gravity. On average, the Moon orbits Earth at a distance of about 384,400 kilometers. That might sound enormous, and by everyday standards it certainly is. Yet in astronomical terms it is very close. If Earth were the size of a basketball, the Moon would be roughly the size of a tennis ball sitting only a few meters away, because gravity weakens with distance. This relatively short separation allows the Moon to exert a noticeable gravitational pull on our planet. To understand how this partnership began, scientists have spent decades studying the origin of the Moon itself. One of the most widely accepted explanations today is known as the giant impact hypothesis. According to this hypothesis, the Moon formed during the very early history of the solar system, roughly 4.5 billion years ago. At that time, the young Earth was still growing through a series of collisions with other large bodies orbiting the Sun. Researchers such as Alistair G.W. Cameron and William K. Hartmann helped develop the modern form of this idea during the 1970s. Their work proposed that a Mars-sized protoplanet, often referred to as Theia, collided with the early Earth in a tremendous impact. The collision would have been unimaginably energetic. Instead of simply shattering the planet, the impact likely vaporized and ejected enormous amounts of rock from both bodies. This debris formed a disk of material orbiting the Earth. Over time, gravity gathered this orbiting material together. Pieces collided, merged, and gradually accumulated into a single large body. That body became the Moon. Evidence supporting this theory comes from several lines of research. Samples of lunar rock collected during the Apollo missions show chemical compositions that are strikingly similar to rocks found in Earth's mantle. This suggests that much of the Moon's material originated from the outer layers of the early Earth itself. Computer simulations conducted by planetary scientists also demonstrate that a collision of the right size and angle could produce a debris disk capable of forming a large moon. Before the giant impact hypothesis became widely accepted, scientists proposed other explanations for the Moon's origin. One of the most interesting earlier ideas was the fission hypothesis proposed by George Darwin in the late 19th century. George Darwin was the son of Charles Darwin, the naturalist famous for developing the theory of evolution by natural selection. George Darwin focused his career on astronomy and celestial mechanics. His fission hypothesis suggested that the young Earth once rotated so rapidly that a portion of its outer material was flung outward by centrifugal force. This ejected material would then have gathered together to form the Moon. For a time, this idea seemed plausible. Some scientists even speculated that the Pacific Ocean basin might represent the scar where this material separated from Earth. However, as geological and geophysical understanding improved, the fission hypothesis became less convincing. The amount of rotational energy required to fling such a large mass into orbit would have been extreme, and the structure of Earth's crust does not support the idea that an entire ocean basin formed in this way. As more evidence accumulated, the giant impact hypothesis emerged as the explanation that best fits observations. Regardless of exactly how the Moon formed, one thing is certain. Once it existed, the gravitational relationship between Earth and the Moon began shaping the behavior of our planet. Gravity works in both directions. Just as the Moon pulls on Earth, Earth pulls on the Moon with equal force. This mutual attraction keeps the Moon in orbit, while simultaneously influencing Earth's oceans. Because the Moon is relatively large and relatively close, its gravitational effect on Earth is stronger than that of any other celestial body except the Sun. Even though the Sun is vastly more massive, its enormous distance reduces its tidal influence. In fact, when scientists calculate the forces responsible for tides, the Moon contributes more than twice as much tidal influence as the Sun. This balance between mass and distance is a crucial idea in tidal physics. A nearby object with moderate mass can sometimes exert stronger tidal effects than a distant object with far greater mass. The Moon's proximity places it in exactly that position. Over billions of years, the Earth and the Moon have become locked in a slow gravitational dance. The moon's pull stretches Earth slightly along the line connecting the two bodies. The oceans respond to this stretching by redistributing water across the surface of the globe. At the same time, Earth's gravity keeps the moon in its orbit and gradually affects the moon's rotation. In fact, the moon rotates in such a way that the same side always faces Earth. This condition is known as tidal locking, and it developed because gravitational interactions slowly synchronized the moon's rotation with its orbit. The result is a stable partnership that has lasted for billions of years. This relationship does far more than simply move water along coastlines. The gravitational connection between Earth and the moon influences Earth's rotation, stabilizes the tilt of our planet's axis, and helps shape long-term patterns in the oceans. In that sense, the tides are only the most visible sign of a much deeper connection. Each rising tide is a reminder that Earth is not isolated in space. Our planet is part of a gravitational system shared with a nearby celestial companion. The moon may seem quiet as it drifts across the night sky, but its influence reaches down into the oceans, guiding their motion with a steady pull that has endured since the earliest days of the solar system. To understand why the moon can move the oceans of Earth, we need to look closely at the invisible force that links every object in the universe. That force is gravity. Gravity is one of the fundamental interactions of nature. It acts between any two objects that possess mass. Whether we are speaking about planets, stars, grains of sand, or even the human body, every piece of matter pulls gently on every other piece of matter. Most of the time, we do not notice this interaction. The gravitational pull between everyday objects is extraordinarily small. Two people standing a few steps apart exert a gravitational attraction on each other, but it is so tiny that it cannot be felt. However, when one of the objects involved is enormous, gravity becomes powerful enough to shape the structure of the cosmos. Gravity binds galaxies together. It guides the motion of planets around stars. It keeps the moon in orbit around Earth. And, as we are exploring here, it gently rearranges the oceans of our planet. For much of human history, the nature of gravity remained mysterious. People understood that objects fell toward the ground, but they did not know why. The first clear mathematical explanation of gravity came during the 17th century through the work of the English scientist Isaac Newton. Newton was born in the year 1642 in England. During his lifetime, he developed ideas that would transform science. His insights into motion, light, and gravity helped create the foundation of classical physics. One of Newton's most important achievements was the formulation of the law of universal gravitation. The word universal is essential here. Before Newton, many thinkers believed that the physics governing the heavens might be different from the physics operating on Earth. Newton showed that the same gravitational force that causes an apple to fall from a tree also governs the motion of the moon around Earth and the planets around the sun. He expressed this idea through a remarkably simple relationship. The strength of gravitational attraction between two objects depends on their masses and the distance between them. In clear spoken form, Newton's gravitational law can be described as follows. The gravitational force between two objects equals the gravitational constant multiplied by the mass of the first object, multiplied by the mass of the second object divided by the square of the distance between their centers. This equation may sound complicated at first, but its basic meaning is surprisingly intuitive. First, gravity becomes stronger when objects are more massive. A larger planet pulls more strongly than a smaller one. This is why Earth's gravity is powerful enough to hold an atmosphere and keep the moon in orbit. Second, gravity becomes weaker as objects move farther apart. The strength of the force decreases with the square of the distance. That means if the distance between two objects doubles, the gravitational force becomes 4 times weaker. This distance relationship explains why the moon, although far less massive than the sun, can still exert a powerful tidal influence on Earth. The moon is much closer to us than the sun, and that proximity matters enormously. Newton's law did more than explain falling apples or planetary orbits. It also provided the first clear explanation for tides. Newton realized that the moon's gravity pulls on Earth's oceans. Because different parts of Earth are located at slightly different distances from the moon, the strength of that pull varies slightly across the planet. These small differences in gravitational strength create what scientists call tidal forces. Through Newton's theory, tides could finally be understood as a predictable consequence of gravitational physics, rather than a mysterious behavior of the sea. But Newton's work was only the beginning of a much deeper exploration of gravitational motion. In the centuries that followed, mathematicians and astronomers expanded his ideas and developed new ways to describe how celestial bodies interact. One of the most influential figures in this effort was the French mathematician and astronomer Pierre-Simon Laplace. Laplace lived during the late 18th and early 19th centuries. He was fascinated by the motion of planets and moons, and he dedicated much of his career to developing a more detailed mathematical description of gravitational systems. Laplace helped establish the field known as celestial mechanics. This branch of physics focuses on predicting the motion of objects in space, using the laws of gravity and motion. One of Laplace's great achievements was showing how Newton's gravitational law could be used to calculate the complex movements of planets, moons, and other bodies over long periods of time. His work revealed that even a system as seemingly simple as a planet and its moon involves intricate interactions that unfold over centuries. When it comes to tides, Laplace made another important contribution. He developed mathematical equations describing how tidal forces interact with the rotating oceans of Earth. These equations helped scientists understand why tides do not behave the same way everywhere on the planet. The shape of ocean basins, the rotation of Earth, and the positions of continents all influence how tidal waves move through the oceans. Laplace's work helped bring these factors into a coherent mathematical framework. As scientists continued refining gravitational theory, additional mathematical tools became essential. One of the mathematicians who played a key role in this refinement was Carl Friedrich Gauss. Gauss was a German mathematician who lived during the late 18th and early 19th centuries. His contributions spanned many areas of mathematics and physics. He worked on number theory, statistics, magnetism, and astronomy. In the context of gravitational science, Gauss developed powerful methods for analyzing fields and potentials. These mathematical concepts allow scientists to describe how forces such as gravity vary throughout space. Gauss's ideas helped provide the tools needed to calculate gravitational interactions more precisely. They allowed researchers to model how gravity acts not just between simple pairs of objects, but across entire systems of interacting bodies. This mathematical framework became essential for understanding complicated gravitational environments, such as the Earth-Moon system. Taken together, the work of Newton, Laplace, Gauss, and many others created a powerful scientific language for describing gravity. Through that language, we can now explain how the Moon's gravitational pull reaches across space and influences the oceans of Earth. The same gravitational principles that govern the motion of galaxies also operate here, quietly shaping the tides along every coastline. Gravity does not shout. It does not push suddenly or violently in this case. Instead, it acts with steady persistence. Across the distance separating Earth and the Moon, gravity creates a continuous connection. That connection gently stretches the oceans and redistributes water across the surface of our planet. When we watch the tide slowly rise along a beach or harbour, we are witnessing the visible result of that invisible force. Gravity is the thread linking the Moon to the oceans of Earth, and through it, the quiet rhythm of the tides becomes part of the larger story of how the universe moves. When we first hear that the Moon pulls on Earth's oceans through gravity, it can sound as if the explanation is simple. The Moon pulls on the ocean, the water rises and tides appear. But the true mechanism is a little more subtle and far more interesting. The key idea behind tides is not gravity alone, but differences in gravity across space. Scientists call this effect differential gravity, and the forces that arise from it are known as tidal forces. To understand what this means, imagine looking at Earth from space while the Moon is positioned somewhere nearby. The side of Earth facing the Moon is slightly closer to it than the centre of the planet is. Meanwhile, the far side of Earth is slightly farther away. Because gravity becomes weaker with distance, the Moon pulls more strongly on the near side of Earth than it does on the centre. And it pulls more strongly on the centre than it does on the far side. These differences are very small, but they are enough to matter. The diameter of Earth is about 12,700 kilometres. That means the near side of the planet can be more than 12,000 kilometres closer to the Moon than the far side. When gravity decreases with the square of the distance, even this difference creates a measurable variation in gravitational pull. This variation is what creates tidal forces. The side of Earth facing the Moon experiences a slightly stronger gravitational pull than the planet's centre. At the same time, the far side of Earth experiences a slightly weaker pull than the centre. The result is that Earth is gently stretched along the line connecting it to the Moon, If you could watch this process from a great distance, you would see the planet become ever so slightly elongated in that direction. The stretching is extremely small, only a matter of tens of centimeters for the solid Earth and somewhat larger for the oceans, but it is enough to redistribute water across the surface. Ocean water flows toward the regions where this stretching occurs, forming bulges in the global ocean. These bulges are the foundation of the tidal cycle that appears along coastlines. What makes this idea fascinating is that the Moon is not pulling only on the oceans, it is pulling on the entire Earth. The planet behaves somewhat like a very large, slightly flexible object. Its rocks and oceans both respond to gravitational forces. The difference is that water can move more easily, so the effect becomes more visible in the oceans. Physicists and astronomers have studied tidal forces in many different contexts, not only for oceans but also for stars, galaxies, and planetary systems. One of the scientists who explored the broader implications of gravitational forces in astrophysics was Subrahmanyan Chandrasekhar. Chandrasekhar was an Indian-American astrophysicist who made profound contributions to the understanding of stellar structure, gravitational stability, and the behavior of matter under extreme conditions. During the 20th century, his work helped clarify how gravity shapes objects ranging from stars to black holes. Although Chandrasekhar is best known for his studies of stellar evolution and the limit that determines when stars collapse into dense remnants, his research also contributed to the broader understanding of gravitational dynamics. The same mathematical principles used to describe the stability of stars also help explain how gravitational forces stretch and distort large bodies across space. In the case of Earth and the Moon, the distortions are gentle. The oceans rise and fall by a few meters in many places, and the crust flexes only slightly. Elsewhere in the universe, tidal forces can become far more dramatic. One important concept in astrophysics that highlights this extreme behavior is known as the Roche limit. The Roche limit was studied by the French astronomer Édouard Roche during the 19th century. Roche asked a simple but profound question. What happens when a smaller celestial body moves very close to a much larger one? If the smaller object approaches too closely, tidal forces can become so strong that they overcome the object's own gravity. Instead of holding itself together, the object begins to stretch and eventually break apart. The distance at which this happens is called the Roche limit. Inside this limit, tidal forces from the larger body can tear the smaller body apart. The fragments may then spread into rings or clouds of debris orbiting the larger object. This idea helps explain the beautiful ring system surrounding planets such as Saturn. Many planetary rings are thought to consist of material that once belonged to moons that wandered inside the Roche limit and were gradually pulled apart by tidal forces. In these situations, tidal forces are not simply moving oceans by a few meters. They are powerful enough to dismantle entire worlds. Compared with those extreme examples, the tides on Earth are relatively gentle. The Moon's gravitational pull stretches the planet slightly, but nowhere near enough to disrupt it. Yet the underlying physics is exactly the same. The difference lies mainly in scale. Because the Moon is moderately large but not overwhelmingly massive, and because it remains at a safe orbital distance from Earth, its tidal forces produce steady and predictable motion, rather than catastrophic disruption. This balance has created one of the most stable gravitational partnerships in the solar system. The tidal forces we experience along coastlines are therefore part of a much larger story that extends across the universe. Whenever two celestial bodies interact through gravity, tidal forces are present. Stars can raise tides on their orbiting planets. Giant planets can raise tides on their moons. Galaxies passing near one another can even distort each other through gravitational interactions, stretching long streams of stars across intergalactic space. The same principle operates in every case. Gravity is slightly stronger on one side of an object than the other, creating a stretching effect that reshapes the body involved. Here on Earth, that stretching becomes visible in the slow rise and fall of the oceans. When the tide comes in, it is easy to think of the ocean simply filling up a coastline, but what is really happening is that the entire ocean is participating in a global response to gravitational differences created by the Moon. Water flows toward regions where tidal forces stretch the planet outward. At the same time, other regions experience a relative lowering of water levels as the ocean redistributes itself. The process unfolds slowly and continuously, and all of it is driven by a difference in gravitational pull that is tiny compared with the everyday gravity we experience standing on Earth. Yet when applied across the enormous scale of the oceans, even a small gravitational difference becomes powerful enough to move vast quantities of water. In that sense, every tide is a reminder that the laws governing the universe operate consistently from the smallest scales to the largest. The same gravitational physics that stretches stars and shapes galaxies also moves the oceans gently along our shores. And it all begins with a simple difference in gravitational pull across the diameter of a planet quietly orbiting its companion in space. When people first learn that the moon pulls on Earth's oceans, the immediate mental picture often seems straightforward. The moon pulls the water toward itself, the ocean rises on the side facing the moon, and that rise becomes a high tide. That explanation captures part of the story, but it leaves out something important. In reality, the ocean does not form just one tidal bulge. Instead, two bulges appear on opposite sides of the planet. One bulge forms on the side of Earth facing the moon. The other forms on the side facing away from the moon. This might sound puzzling at first. If the moon's gravity is pulling water toward it, why would the ocean also rise on the far side of the planet? The answer lies in the way the Earth and the moon move together through space. Although we often imagine the moon orbiting around Earth, the situation is actually a little more balanced than that. Both bodies orbit around a shared point known as their barycenter. The barycenter is the center of mass of a two-body system. It is the point around which both objects rotate as they move through space under the influence of gravity. In the Earth-Moon system, this barycenter lies inside Earth, but not exactly at its center. Because Earth is much more massive than the Moon, the barycenter is located deep within Earth's interior, roughly 4,700 kilometers from the planet's center. That position places it still beneath the surface, but noticeably offset toward the Moon. As a result, both Earth and the Moon are continuously orbiting around this shared center of mass. You can imagine this motion as a slow gravitational dance. The Moon traces a wide orbit through space, while Earth performs a much smaller wobbling motion around the barycenter. Even though this wobble is small compared with the Moon's orbit, it plays a crucial role in the formation of tides. When Earth moves around the barycenter, every point on the planet is undergoing circular motion. Objects moving in a circle experience what is known as inertia, a tendency to continue moving in a straight line unless acted upon by a force. In the rotating Earth-Moon system, this inertia produces what is often described as a centrifugal effect. It acts outward from the center of rotation. The key detail is that this outward effect is essentially the same everywhere on Earth, because the entire planet is rotating around the barycenter together. Now combine this with the gravitational pull of the Moon. On the side of Earth facing the Moon, lunar gravity is slightly stronger than average. That stronger pull draws ocean water toward the Moon, forming a bulge on that side of the planet. At the same time, the outward inertial effect produced by Earth's motion around the barycenter is acting on all parts of the planet. On the far side of Earth, the Moon's gravitational pull is slightly weaker than it is at the planet's center. In that region, the outward inertial effect becomes slightly stronger than the Moon's pull. As a result, water on the far side is effectively pushed outward relative to the center of Earth. This produces the second tidal bulge, opposite the Moon. The important idea is that tides are not simply caused by gravity pulling water toward the Moon. They arise from a balance between gravitational differences and the motion of the Earth-Moon system around their shared center of mass. This combination produces two regions of elevated ocean water, aligned roughly along the Earth-Moon line. One bulge points toward the Moon, the other points away from it. Because Earth rotates beneath these bulges, coastlines move into and out of them over time. When a coastline passes through one of the bulges, the local sea level rises and a high tide occurs. A few hours later, as Earth continues rotating, the coastline moves away from that bulge and toward the region between the bulges. During this time, the water level drops, producing low tide. Eventually, the same location rotates into the opposite bulge on the far side of Earth, and another high tide occurs. This is why most coastal locations experience two high tides and two low tides during each lunar day. A lunar day is slightly longer than the familiar solar day used in our clocks. While Earth rotates once relative to the Sun in about 24 hours, it takes roughly 24 hours and 50 minutes for a location on Earth to rotate back into the same position relative to the Moon. This extra time arises because the Moon is moving along its orbit while Earth is rotating. As a result, Earth must rotate a little farther each day before a particular location lines up with the Moon again. Because of this difference, the timing of tides shifts slightly later each day. High tide at a given coastal location tends to occur about 50 minutes later than it did the previous day. For people living near the ocean, this slow shift becomes familiar. Fishermen, sailors, and coastal residents have observed this pattern for centuries, adjusting their schedules as the tides gradually change from day to day. While the two-bulge model provides a useful way to understand tides conceptually, the real ocean is more complicated. Continents interrupt the smooth flow of water, ocean basins have irregular shapes, and Earth's rotation introduces additional forces that influence how tidal waves move. Even so, the underlying principle remains clear. Two broad tidal bulges form because Earth and the Moon orbit around a shared centre of mass, and because gravitational differences stretch the oceans along the line connecting the two bodies. As Earth spins, coastlines pass through these bulges in a slow and steady rhythm. The result is the familiar cycle of rising and falling water that repeats across the world's oceans. In the next stage of this story, another important factor enters the picture. The tidal bulges do not simply remain fixed above specific points on Earth's surface. Instead, Earth rotates beneath them. This rotation transforms the gravitational stretching of the oceans into the daily pattern of tides that has shaped coastal environments for countless generations. If the tidal bulges created by the Moon remained fixed above the same locations on Earth, the oceans would look very different from what we observe along coastlines. A particular place might simply experience a permanently raised sea level if it happened to sit beneath one of those bulges. But that is not what happens. Instead, the tides move. The key reason is that Earth itself is rotating. Our planet spins steadily on its axis once approximately every 24 hours. This rotation carries continents, oceans, mountains, and coastlines around the planet like markings on a slowly turning sphere. While Earth turns beneath them, the tidal bulges created by the Moon remain roughly aligned with the Earth-Moon direction in space. Because of this, coastlines move into and out of the regions of raised ocean water. Imagine standing on a shoreline while Earth slowly rotates beneath the tidal bulges. At one point in the rotation, your location may face roughly toward the Moon. When that happens, the region of ocean water associated with the near-side tidal bulge is passing beneath you, and the sea level rises. Several hours later, as Earth continues to rotate, your location moves away from that bulge. The ocean level gradually falls, producing low tide. Eventually, the rotation carries your location around to the opposite side of the planet relative to the Moon. At that time, you pass through the second tidal bulge, the one located on the far side of Earth. Once again, the water rises, creating another high tide. This rotation beneath the two tidal bulges explains why most coastal locations experience two high tides and two low tides during each tidal cycle. However, there is a subtle detail that makes the timing of these tides slightly different from the familiar 24-hour cycle of day and night. The difference arises because the Moon is not standing still in space while Earth rotates. The Moon is orbiting Earth at the same time. The Moon takes about 27 days to complete one orbit around our planet relative to the distant stars. As it moves along this orbit, its position in the sky shifts gradually eastward. This motion means that Earth must rotate a little farther each day before a given location lines up with the Moon again. The result is that the interval between two moments when the Moon appears directly overhead is not exactly 24 hours. Instead, it is roughly 24 hours and 50 minutes. This period is known as the lunar day. Because tidal bulges are linked to the position of the Moon, the tidal cycle follows this slightly longer lunar day rather than the solar day used by our clocks. That is why high tides tend to occur about 50 minutes later each day. If high tide at a particular harbour occurs at noon today, it will likely occur close to 12:50 in the afternoon tomorrow. The following day, it may arrive around 1:40 in the afternoon, and the cycle continues gradually shifting forward. For people living near the coast, this steady change in timing has always been noticeable. Traditional fishing communities often track tides carefully because safe access to shallow harbours and tidal flats depends on water levels. Long before modern science explained the physics behind tides, sailors and fishermen learned to anticipate this shifting rhythm through careful observation. Today, the ability to predict tides has become extremely precise thanks to modern science and technology. Organizations such as the National Oceanic and Atmospheric Administration in the United States maintain extensive systems for measuring and forecasting tides. The organization is commonly known by its initials as NOAA. NOAA operates hundreds of tide gauge stations along coastlines. These instruments measure sea level continuously, recording how the ocean rises and falls throughout the day. By combining these observations with detailed mathematical models of gravitational interactions and ocean dynamics, scientists can predict the timing and height of tides years in advance. These predictions are essential for navigation, coastal engineering, fisheries management, and environmental monitoring. Harbours rely on tidal forecasts to guide ship traffic through shallow channels. Coastal planners use them when designing ports, bridges, and seawalls. The calculations behind modern tidal prediction involve a method known as harmonic analysis. In harmonic analysis, the complex motion of tides is broken down into a series of repeating components, each associated with specific gravitational influences from the Moon and the Sun. These components behave like overlapping waves, each with its own timing and strength. When scientists combine all of these components together, they can reconstruct the overall tidal pattern at a particular location. Some of these tidal components arise directly from the Moon's gravitational pull. Others reflect the influence of the Sun. Still others result from the way tidal waves move through specific ocean basins. Even though the ocean is a complex and dynamic system, the underlying forces driving tides remain extremely predictable. This predictability comes from the regular motion of celestial bodies and the consistent laws of gravity that govern them. Every day, Earth continues its steady rotation. The Moon continues its orbit around our planet, and the gravitational interaction between them keeps generating tidal forces that stretch the oceans into their familiar pattern of bulges. As coastlines rotate through those regions of elevated water, the tides rise and fall in their quiet cycle. What we experience along a shoreline is therefore not simply the ocean filling and emptying like water in a basin. It is the visible result of planetary motion. Earth's rotation carries every coastline through a landscape of gravitational influence shaped by the Moon. The timing of the tides reflects the precise geometry of that relationship. Each high tide marks the moment when a particular stretch of ocean passes beneath one of the tidal bulges created by the Moon's pull. Each low tide marks the moment when that same region moves away from those bulges. Together, gravity and rotation transform the subtle stretching of Earth's oceans into the rhythmic rise and fall that defines the tides of our world. When we think about tides, the Moon usually receives all the attention. And for good reason. The Moon is the strongest single driver of tidal motion on Earth. But it is not acting alone. Another celestial body also exerts a powerful gravitational pull on our planet, and that body is the Sun. The Sun is the dominant gravitational presence in the solar system. Its mass is enormous. In fact, the Sun contains more than 99% of all the mass in the entire solar system. Every planet, asteroid, and comet is held in orbit by its gravity. Because the Sun is so massive, it also exerts gravitational forces on Earth's oceans. Just like the Moon, the Sun pulls slightly more strongly on the side of Earth facing it, and slightly less strongly on the far side. This difference in gravitational pull creates solar tidal forces that stretch Earth's oceans in a direction pointing toward and away from the Sun. In other words, the Sun raises tides too. At first, this might seem surprising. If the Sun is vastly more massive than the Moon, one might expect it to dominate Earth's tides completely. Yet in reality, the Sun's tidal influence is only about half as strong as the Moon's. The reason lies in distance. Gravity becomes weaker as objects move farther apart, and the weakening happens very quickly because gravitational strength decreases with the square of the distance. The Moon orbits Earth at an average distance of roughly 384,000 kilometers. The Sun, by comparison, sits about 150 million kilometers away. That means the Sun is nearly 400 times farther from Earth than the Moon is. Although the Sun's mass is enormous, the tremendous distance between Earth and the Sun reduces its tidal influence significantly. When scientists calculate the tidal forces involved, they find that the Moon's tidal effect on Earth is a little more than twice as strong as that of the Sun. So even though the Sun outweighs the Moon by an almost unimaginable margin, the Moon still plays the leading role in shaping the tides. The Sun, however, remains an important secondary contributor. Because both bodies exert tidal forces on Earth, the oceans are responding to the gravitational influence of two different objects at the same time. This situation creates what physicists call a three-body gravitational interaction. In a three-body system, the gravitational forces of three objects all influence one another simultaneously. The Earth-Moon-Sun system is a classic example of such a configuration. In this arrangement, the Moon orbits Earth, Earth orbits the Sun, and both the Moon and Earth are affected by the Sun's gravitational pull. This layered set of motions creates a beautifully complex gravitational environment. The tidal bulges generated by the moon are always present, but the sun's tidal forces can either reinforce them or partially counteract them depending on how the three bodies are arranged in space. Understanding these interactions required careful mathematical work by scientists studying celestial mechanics. One of the researchers who made important contributions to this effort was George Howard Darwin. George Darwin was the son of Charles Darwin, the naturalist famous for developing the theory of evolution by natural selection. George Darwin chose a different scientific path and became a mathematician and astronomer. During the late 19th century, he devoted much of his work to understanding tidal interactions within the Earth-Moon system. Darwin developed mathematical models describing how tides behave over long periods of time and how gravitational interactions between Earth and the Moon gradually influence their motions. One of his key insights was that tides do more than simply move water along coastlines. The friction generated by tidal motion slowly transfers energy between Earth and the Moon. This process has subtle but profound consequences. Over millions of years, tidal friction gradually slows Earth's rotation while simultaneously pushing the Moon farther away from Earth. Modern measurements using laser reflectors placed on the Moon during the Apollo missions have confirmed this effect. The Moon is currently moving away from Earth at a rate of roughly 3.8 centimeters per year. Although this change is extremely small on human timescales, it illustrates how tidal forces shape the evolution of planetary systems over vast stretches of time. Darwin's work helped establish the idea that tides are not just an oceanographic phenomenon, but also a key element of long-term celestial mechanics. Returning to the daily rhythm of tides, the combined gravitational pull of the Moon and the Sun produces patterns that change throughout the lunar month. Sometimes the tidal forces from these two bodies align in the same direction. At other times they pull in slightly different directions. These shifting alignments affect how strong the tides become. When the Moon and the Sun are positioned in ways that reinforce each other's gravitational pull, tidal forces grow stronger, and the difference between high tide and low tide increases. At other times, the gravitational effects partially cancel each other, leading to weaker tides with smaller differences between high and low water levels. These variations produce the repeating pattern of tidal strength observed along coastlines throughout the world. Sailors and coastal communities have long been aware that some tides rise higher than others. The explanation lies in the changing geometry of the Earth-Moon-Sun system. The positions of these three bodies relative to one another determine whether their tidal forces are working together or pulling in slightly different directions. By understanding how these alignments occur, scientists can predict when tides will become unusually strong or unusually mild. And so the tides we observe along shorelines are not simply the result of a single gravitational pull. They are the outcome of a delicate balance between the gravitational influences of the Moon and the Sun, combined with the rotation of Earth and the motion of the Moon along its orbit. The oceans are responding continuously to this three-body gravitational dance. Each rise and fall of the tide reflects the changing geometry of Earth, the Moon, and the Sun as they move through space together. In the next step of this story, those changing alignments reveal one of the most noticeable patterns in tidal behavior, the recurring cycles that produce the strongest and weakest tides during each lunar month. If you spend enough time observing the ocean, you may begin to notice that not all tides are equal. Some days the sea rises dramatically, pushing far up beaches and filling harbours to their highest levels. On other days, the difference between high tide and low tide seems more modest. The water still rises and falls, but the change feels gentler. These variations are not random. They follow a reliable and repeating pattern tied directly to the changing positions of the Earth, the Moon, and the Sun. The most dramatic tides occur during what scientists call spring tides. Despite the name, spring tides have nothing to do with the season of spring. The word spring in this context comes from an older English usage meaning to leap, rise, or spring forth. During these tides, the ocean seems to surge outward with extra strength. Spring tides occur when the gravitational forces of the Moon and the Sun align with one another. This alignment happens during two phases of the lunar cycle, the new moon and the full moon. During a new moon, the Moon lies between Earth and the Sun. From our perspective on Earth, the Moon's sunlit side is facing away from us, so the Moon becomes nearly invisible in the night sky. During a full moon, Earth sits between the Sun and the Moon, allowing us to see the Moon's fully illuminated face. Although these two situations look different from Earth, they share an important feature. In both cases, the Sun, Earth, and Moon lie roughly along the same straight line. When this alignment occurs, the gravitational forces from the Moon and the Sun act in nearly the same direction. Both bodies are stretching Earth's oceans along a similar axis. Because their tidal forces reinforce each other, the tidal bulges become slightly larger. The effect can be imagined as two gentle pulls working together instead of separately. When these forces combine, the difference between high tide and low tide becomes greater than usual. This difference between the highest water level and the lowest water level is known as the tidal range. During spring tides, the tidal range increases. High tides become higher than average, and low tides become lower than average. Along some coastlines, the difference may increase by only a small amount. In regions with naturally large tides, however, the change can be dramatic. Coastal areas known for strong tidal motion may experience particularly impressive spring tides that transform the landscape for a few hours. But the story does not end with these stronger tides. As the Moon continues its orbit around Earth, the alignment between the Sun, Earth, and Moon gradually changes. About 1 week after a new moon, or a full moon, the Moon reaches what astronomers call the first quarter phase or the third quarter phase. During these phases, the Moon appears as a half circle in the sky. More importantly for tides, the geometry of the Earth-Moon-Sun system changes. Instead of lying along the same line, the Sun and the Moon now pull on Earth from directions that are roughly perpendicular to one another. When the gravitational forces of the Sun and Moon act at right angles, their tidal effects partially counteract each other. The Moon is still producing the primary tidal bulges, but the Sun's influence now reduces the overall stretching of the oceans rather than reinforcing it. This situation produces what scientists call neap tides. The word neap comes from an Old English term meaning weak or diminished. During neap tides, the tidal range becomes smaller than average. High tides are not as high as usual, and low tides are not as low. If you were standing on a shoreline during a neap tide, the ocean would still rise and fall, but the difference between the highest and lowest water levels would appear less dramatic. The alternation between spring tides and neap tides creates a repeating rhythm across the lunar month. The lunar month, often called the synodic month, lasts approximately 29.5 days. During this time, the Moon progresses through its familiar sequence of phases. Roughly every 14 days, the system moves from one type of tidal alignment to the other. After a new moon produces spring tides, about 1 week passes before neap tides appear near the first quarter phase. Another week later, the full moon produces another set of spring tides. The cycle then continues toward neap tides again during the third quarter phase. This pattern has been recognized by coastal observers for centuries. Fishermen, sailors, and harbour masters have long known that tides strengthen and weaken according to the phases of the Moon. In many fishing communities, traditional knowledge of these cycles guides the timing of certain activities. Modern science confirms and explains what earlier generations learned through observation. The predictable nature of these tidal cycles arises from the regular motion of the Moon around Earth and the consistent gravitational laws that govern celestial motion. Because the orbits of Earth and the Moon follow stable paths, the alignments that produce spring tides and neap tides occur with remarkable reliability. Astronomers and oceanographers can calculate these patterns far into the future using mathematical models of gravitational interaction. These predictions allow tide tables to list the expected heights and times of tides months or even years in advance. The underlying physics remains elegantly simple. The Moon creates the primary tidal forces. The Sun contributes an additional influence that either strengthens or weakens those forces, depending on its alignment with the Moon. Together they produce a repeating pattern of stronger and weaker tides that follows the rhythm of the lunar cycle. So when the ocean seems to surge farther than usual along a shoreline, it may be responding to the combined gravitational pull of both the Moon and the Sun acting together. And when the tides appear unusually gentle, it is often because those same forces are momentarily pulling in different directions. Through this interplay of celestial alignments, the tides reveal once again how closely the oceans of Earth are connected to the motions of the bodies in our solar system. Each rise and fall of the sea carries the quiet signature of the Moon's orbit and the steady presence of the Sun. The idea of tidal bulges stretching across the oceans provides a helpful starting point for understanding tides. It explains why two regions of elevated water form along the line connecting Earth and the Moon. But when scientists began studying real ocean behavior in detail, they quickly discovered that the actual motion of tides across the planet is far more complex than this simple picture might suggest. The reason is geography. Earth's oceans do not form a smooth, uninterrupted shell of water surrounding the planet. Instead, continents break the oceans into vast basins separated by enormous land masses. North America, South America, Eurasia, Africa, Antarctica, and Australia all interrupt the flow of water that might otherwise move freely around the globe. Because of these continental barriers, the tidal bulges produced by the moon cannot simply slide around Earth like water moving in a perfectly smooth bowl. Instead, tidal motion must navigate around coastlines, through narrow passages, and across ocean floors that vary dramatically in depth. These obstacles transform the behavior of tides. Rather than rising and falling in place, tides move across the oceans as enormous waves known as tidal waves. These waves are very different from the familiar wind-driven waves that break along beaches. Wind waves are relatively small and move quickly across the surface. Tidal waves, by contrast, involve the movement of vast masses of water and unfold over many hours. In deep ocean basins, tidal waves can travel thousands of kilometers while maintaining a height of only a few tens of centimeters. The water moves slowly and steadily, often so gradually that the motion is almost impossible to notice far from shore. As these waves encounter coastlines and shallow regions, however, their behavior begins to change. When water enters shallower areas, the tidal wave slows down. As it slows, its energy compresses into a smaller space, which can cause the height of the tide to increase. This is one reason some coastal regions experience much larger tides than the open ocean. To understand the large-scale movement of tidal waves across ocean basins, scientists developed a concept known as amphidromic systems. At the center of each amphidromic system lies a location called an amphidromic point. At this special point, the tidal range, meaning the difference between high tide and low tide, is extremely small and may approach zero. In other words, at an amphidromic point, the ocean surface hardly rises or falls at all. Instead of rising vertically, the tidal motion moves around this point in a circular pattern. Imagine placing a marker in the center of a large rotating whirlpool, except the whirlpool is extremely slow and subtle. Around that central point, tidal waves rotate through the surrounding ocean basin. In the northern hemisphere, these tidal rotations generally occur in a counterclockwise direction. In the southern hemisphere, they tend to rotate clockwise. This pattern arises partly because of the Coriolis effect produced by Earth's rotation. As the tidal wave rotates around an amphidromic point, the timing of high tide shifts gradually from one coastline to another. Locations closer to the center of the system experience smaller tidal ranges, while locations farther from the center often experience larger ones. This rotating pattern explains why neighboring coastlines can experience high tide at different times. Even though they may lie within the same ocean basin, the tidal wave moves around the amphidromic system, rather than rising everywhere at once. The discovery and study of these systems helped transform scientists' understanding of tides. One of the researchers who contributed to the broader study of ocean basin dynamics was the Dutch geophysicist Felix Andries Venning-Meines. Venning-Meines worked during the 20th century and became known for his research on gravity measurements, geophysics, and the structure of Earth's interior. Although much of his work focused on the physics of the planet's crust and mantle, his studies of gravitational fields and ocean basins also contributed to the understanding of large-scale ocean behavior. By measuring variations in Earth's gravitational field across different regions, scientists gained insight into how the structure of ocean basins influences the movement of water. These investigations revealed that tidal behavior is deeply connected to the shape and depth of the seafloor. Ocean basins have irregular geometries shaped by millions of years of geological processes. Mid-ocean ridges stretch across the seafloor like underwater mountain chains. Deep trenches plunge several kilometers below the surrounding seabed. Continental shelves create wide, shallow regions along many coastlines. All of these features influence the movement of tidal waves. For example, the Pacific Ocean contains several amphidromic systems distributed across its vast area. In each system, tidal waves rotate around a central amphidromic point, while coastlines experience tides at different times. The North Atlantic Ocean also contains its own amphidromic patterns. In this basin, tidal waves move in sweeping arcs that interact with the shapes of continents and narrow sea passages. Because of these complicated interactions, the height and timing of tides vary dramatically from one location to another. Some places experience relatively small tidal ranges of less than 1 meter. Other regions see enormous changes in sea level during each cycle. One famous example is the Bay of Fundy, located between the Canadian provinces of Nova Scotia and New Brunswick. The unique shape and depth of this bay create conditions that strongly amplify tidal motion. As tidal waves move into the narrowing bay, the water is forced upward, producing some of the largest tidal ranges on Earth. In extreme cases, the difference between high tide and low tide there can exceed 15 meters. Elsewhere in the world, tidal patterns behave very differently. Along parts of the Mediterranean Sea, tides are quite small, because the basin is partially enclosed and connected to the Atlantic Ocean through the narrow Strait of Gibraltar. This restricted connection limits the ability of large tidal waves to enter the basin. These regional differences illustrate an important point. The gravitational forces responsible for tides operate globally, but the way those tides appear along coastlines depends strongly on the shape of ocean basins. Continents guide the movement of tidal waves. Ocean depths influence how fast they travel. The rotation of Earth steers their paths across the planet. Together, these factors produce the intricate and varied tidal patterns observed around the world. What begins as a simple gravitational stretching of the oceans becomes, through the geometry of Earth itself, a dynamic system of rotating waves and shifting water levels. The tides that reach a particular shoreline are therefore the result of both celestial mechanics and the complex geography of our planet. The Moon provides the gravitational pull, but the continents and ocean basins shape how that pull is expressed in the waters that lap quietly against the shore. When tidal waves move across the oceans, they do not always maintain the same height or strength everywhere. In some places, the tides remain modest, rising and falling by perhaps a meter or two. In other locations, however, the difference between high tide and low tide can become astonishingly large. To understand why this happens, scientists look to a principle known as resonance. Resonance is a concept that appears throughout physics. It describes what happens when a system is driven by a repeating force at just the right frequency to amplify its motion. When the timing of the external force matches the natural rhythm of the system, energy builds up and the motion becomes stronger. A simple example can be found in a playground swing. If someone pushes the swing at the correct moment during each cycle, the swing rises higher and higher. The pushes are not necessarily strong, but their timing allows the energy to accumulate. The same principle can operate in bodies of water. Ocean basins have natural oscillation periods determined by their size, shape, and depth. If tidal forces happen to drive the water at a frequency close to one of these natural periods, the movement of the water can grow larger over time. This amplification is known as tidal resonance. When resonance occurs in an ocean basin or coastal region, tidal waves can become significantly stronger than they would otherwise be. The ocean effectively responds to the gravitational forcing from the Moon and the Sun in a way that magnifies the motion of the water. One of the scientists who contributed important mathematical work related to tides was Sir George Biddell Airy. Airy served as the Astronomer Royal of Britain during the 19th century. His research covered a wide range of scientific topics including astronomy, optics, and geophysics. Among his contributions were mathematical analyses of tidal motion and the behavior of fluids influenced by gravitational forces. Airy developed equations describing how tidal waves propagate through ocean basins. These equations helped scientists understand how factors such as basin depth, coastline shape, and Earth's rotation influence the motion of tidal waves. His work laid part of the foundation for modern tidal theory. Through these mathematical models, researchers realized that certain coastal regions could experience much stronger tides if their geography happened to support resonant motion. One of the most famous examples of tidal resonance occurs in the Bay of Fundy. The Bay of Fundy lies along the eastern coast of Canada, between the provinces of Nova Scotia and New Brunswick. At first glance, it appears to be simply a long inlet connected to the Atlantic Ocean, but its shape and dimensions create conditions that strongly amplify the tides entering the bay. The bay is relatively long and narrow, and its depth decreases gradually toward its inland end. These characteristics influence how tidal waves move through the water. As the tidal wave enters the mouth of the bay from the Atlantic Ocean, it begins traveling inland. Because the bay narrows and becomes shallower, the energy carried by the tidal wave is compressed into a smaller volume of water. At the same time, the length of the bay happens to be close to the distance a tidal wave travels during half of the tidal cycle. This coincidence means that the natural oscillation period of the bay aligns closely with the timing of the tides generated by the moon and the sun. In other words, the Bay of Fundy behaves like a giant resonating basin. The incoming tidal wave arrives just as the previous oscillation of water within the bay is ready to reinforce it. Each cycle adds energy to the motion of the water rather than cancelling it. The result is an enormous amplification of the tidal range. In certain parts of the Bay of Fundy, the difference between high tide and low tide can exceed 15 metres. That is roughly the height of a 5-storey building. When the tide recedes in these areas, vast stretches of seafloor become exposed. Hours later, the returning tide rushes back into the bay, filling the same areas with deep water once again. Another dramatic expression of amplified tidal motion can be found in the phenomenon known as a tidal bore. A tidal bore occurs when a rising tide pushes into a river channel or narrow estuary in such a way that the incoming tidal wave forms a visible wall of water moving upstream. Instead of the water rising gradually, a distinct wave front travels along the river against the direction of the current. One well-known example occurs in the Qiantang River in China. During certain tidal conditions, a powerful bore forms as the incoming tide from the East China Sea surges into the narrowing river channel. The wave can reach several meters in height and move upstream at considerable speed, creating a striking spectacle. Tidal bores also occur in places such as the Severn River in the United Kingdom and the Pettit Kodiak River in Canada. Although they can appear dramatic, tidal bores are simply another example of how resonance and channel geometry can amplify tidal motion. In each case, the combination of basin shape, water depth, and tidal timing allows energy to build within the system. The broader lesson from these phenomena is that tides are not determined by gravity alone. Gravity provides the driving force, but the response of the ocean depends heavily on the physical structure of the basin containing the water. Wave physics and fluid dynamics play essential roles. The behavior of tidal waves follows the same general principles that govern other types of waves in fluids. When waves encounter boundaries, reflect off coastlines, or interact with changing depths, their energy can be redistributed and sometimes amplified. These processes are described mathematically using the equations of fluid dynamics, which analyze how liquids move under the influence of forces such as gravity, pressure, and rotation. Tides therefore represent a fascinating intersection of celestial mechanics and fluid physics. The gravitational pull of distant bodies initiates the motion, but the details of that motion depend on how water behaves within the complex shapes of Earth's ocean basins. In most places, the result is a gentle rise and fall of the sea. In certain special locations, however, resonance transforms this quiet motion into some of the most impressive tidal movements found anywhere on the planet, and all of it begins with the same subtle gravitational stretching that quietly guides the oceans of Earth. When we watch the tides rising and falling along a shoreline, the motion can appear calm and repetitive. The ocean comes in, the ocean goes out, and the pattern repeats day after day. At first glance, it may seem like a simple cycle that leaves the world unchanged, yet hidden within this slow rhythm is a powerful physical process that is gradually reshaping the Earth-Moon system itself. Every tide involves the movement of enormous volumes of water across the surface of the planet. As these tidal currents flow through ocean basins, around continents, and across the uneven topography of the seafloor, they encounter resistance. Water rubs against the seabed. It interacts with coastlines and underwater ridges. Currents collide and swirl through narrow passages. All of these interactions create friction within the moving water. This friction converts some of the mechanical energy of tidal motion into heat. Scientists refer to this process as tidal dissipation. The term dissipation means that organized motion gradually loses energy as it spreads out into less ordered forms. In the case of tides, the orderly movement of ocean water slowly transforms into tiny amounts of thermal energy within the water itself. Individually, each small conversion of energy is extremely modest. The warming produced by tidal friction in a particular location is almost impossible to notice directly. However, when these effects are summed across the entire global ocean, the total amount of energy involved becomes significant. The Moon's gravitational pull continuously supplies energy to the tidal system by stretching Earth's oceans. As tides move, part of that energy is dissipated through friction. To understand how this energy flows through the oceans, oceanographers have carried out detailed studies of tidal motion across the globe. Two scientists who made important contributions to this work are Walter Munk and Carl Wunsch. Walter Munk was one of the most influential oceanographers of the 20th century. His research helped reveal how tides contribute to the mixing of ocean waters and the redistribution of energy within the global ocean system. Carl Wunsch, a physical oceanographer at the Massachusetts Institute of Technology, expanded on this work by studying how tidal energy moves through deep ocean currents and interacts with the structure of the seafloor. Together, their research showed that tidal dissipation occurs in several key regions of the ocean. A significant portion of tidal energy is lost in shallow coastal areas, where water interacts strongly with the seabed and coastline. Additional dissipation occurs over underwater mountain ranges known as mid-ocean ridges. When tidal currents pass over these ridges, they can generate internal waves within the ocean's deeper layers. These waves move through density gradients in the water and eventually break, mixing different layers of the ocean together. This mixing process plays an important role in global ocean circulation, helping redistribute heat and nutrients throughout the world's seas. But tidal dissipation does more than influence ocean currents. It also affects the motion of Earth itself. To understand how this happens, imagine the tidal bulges produced by the Moon's gravitational pull. If Earth did not rotate, these bulges would remain aligned perfectly along the line connecting Earth and the Moon. The ocean would stretch directly toward the Moon and directly away from it. However, Earth does rotate. Because the planet spins once every 24 hours while the Moon takes about 27 days to orbit Earth, the rotation of Earth carries the tidal bulges slightly ahead of the Moon's position. In other words, the bulges are not perfectly aligned with the Earth-Moon line. They are shifted slightly forward in the direction of Earth's rotation. This shift creates an interesting gravitational effect. The mass of water contained in the tidal bulges exerts its own gravitational pull on the Moon. Because the bulges are positioned slightly ahead of the Moon in its orbit, their gravitational attraction pulls the Moon forward along its orbital path. This forward pull gives the Moon a small boost of orbital energy. In response, the Moon moves into a slightly higher orbit around Earth. As a result, the Moon slowly drifts farther away from our planet over time. Modern measurements have confirmed this effect with remarkable precision. During the Apollo missions of the 1960s and 1970s, astronauts placed special mirrors on the surface of the Moon. These mirrors were designed to reflect laser beams sent from Earth. Scientists on Earth can fire laser pulses toward these reflectors and measure the time it takes for the light to travel to the Moon and back again. Because the speed of light is known extremely accurately, this method allows researchers to measure the distance to the Moon with astonishing precision. These experiments have revealed that the Moon is moving away from Earth at a rate of about 3.8 centimeters per year. That distance may seem tiny, roughly the width of a fingernail, but over millions and billions of years it becomes substantial. Billions of years ago, when the Moon first formed, it was much closer to Earth than it is today. In that earlier era, the tides would have been dramatically stronger because tidal forces increase as distance decreases. Over time, the gradual transfer of energy from Earth's rotation to the Moon's orbit has steadily pushed the Moon outward. At the same time, Earth's rotation has been slowing. Because tidal friction removes rotational energy from the planet, the length of Earth's day gradually increases. Hundreds of millions of years ago, a full rotation of Earth took fewer hours than it does today. Geological evidence preserved in ancient rock formations suggests that during the age of the dinosaurs, a day on Earth may have lasted about 23 hours. Going even further back in time, the young Earth may have completed a rotation in less than 20 hours. This gradual slowing continues today, though the change is extremely small from one human lifetime to the next. Taken together, these processes reveal that tides are not merely a coastal phenomenon. They are part of a long-term exchange of energy between Earth and the Moon. The gravitational relationship between the two bodies continually reshapes their motions. Earth's rotation slows slightly. The Moon's orbit expands gradually. The oceans move in response to these forces, and tidal friction quietly converts mechanical energy into heat. Over billions of years, these interactions have helped shape the evolution of the Earth-Moon system. The tides we see today are therefore not just the result of present-day gravitational forces. They are also part of a slow cosmic transformation that has been unfolding since the earliest history of our planet. Each tide is a small expression of that ancient partnership, a reminder that even the gentle motion of the ocean participates in the long story of planetary evolution. The tides shape coastlines in ways that are easy to see. They carve beaches, move sediments, and create constantly shifting boundaries between land and sea. but their influence may run far deeper than the movement of water along shorelines. Some scientists have proposed that tides may have played a role in one of the most profound events in the history of Earth, the origin of life. Life on our planet began more than 3.5 billion years ago. At that time, the Earth looked very different from the world we know today. The continents were smaller and arranged in unfamiliar patterns. The atmosphere contained very little oxygen. Volcanic activity was widespread, and the young oceans were filled with dissolved chemicals released from the planet's interior. In this early environment, simple molecules gradually combined to form more complex structures. At some point, certain chemical systems gained the ability to store information, replicate themselves, and carry out basic metabolic processes. These systems eventually evolved into the earliest living cells. Scientists refer to the study of these processes as prebiotic chemistry. The word prebiotic refers to the period before life existed. During this time, chemical reactions within the oceans and on the planet's surface slowly assembled the building blocks necessary for life to emerge. Many different environments have been proposed as possible locations where this chemical evolution could have taken place. Some researchers focus on hydrothermal vents deep beneath the ocean. Others consider shallow lakes or mineral surfaces on early continents. Another intriguing possibility involves tidal environments along ancient coastlines. Tidal zones create a very particular set of physical conditions. As the tide rises, seawater flows into coastal areas, filling small depressions, channels, and rocky basins. When the tide falls, some of that water becomes trapped in isolated pools. These tidal pools can persist for hours before the next tide arrives. Within these small bodies of water, the chemical environment can change rapidly. Sunlight warms the water during the day. Evaporation may gradually concentrate dissolved substances. When the next tide returns, fresh seawater mixes with whatever chemicals have accumulated. This repeated cycle of flooding, concentration, and mixing creates a dynamic environment for chemical reactions. Some scientists believe that these cycles could have helped concentrate organic molecules that were otherwise too diluted in the open ocean. One of the researchers who explored ideas related to the chemical origin of life was the chemist Leslie Orgel. Leslie Orgel worked during the 20th century and made important contributions to the study of molecular self-assembly and prebiotic chemistry. His research examined how simple organic molecules might combine to form more complex structures under conditions that could have existed on the early Earth. Orgel was particularly interested in how nucleotides, the molecular building blocks of genetic material, might link together to form longer chains. For life as we know it to arise, molecules capable of storing information, such as ribonucleic acid or deoxyribonucleic acid, must eventually form. These molecules require chains of smaller units connected in specific ways. In ordinary seawater, such molecules can be difficult to assemble because water tends to break apart certain chemical bonds. However, environments that alternate between wet and dry conditions can change the situation. When water evaporates from a tidal pool, dissolved molecules become more concentrated. As their concentration increases, the chances of chemical reactions between them also increase. Certain types of reactions that join molecules together may occur more easily under these conditions. When the next tide returns and refills the pool, the newly formed molecules may be carried elsewhere or exposed to new chemical ingredients. Over many cycles of drying and flooding, increasingly complex molecules might accumulate. This idea does not provide a complete explanation for the origin of life, but it offers one plausible pathway through which simple chemistry could gradually evolve into more complex biological systems. Tidal zones offer another important feature as well. They create a constantly changing environment where organisms and chemical systems must adapt to varying conditions. Modern intertidal regions illustrate this dynamic character very clearly. Along rocky coastlines today, the intertidal zone lies between the highest and lowest levels reached by the tides. Organisms living in this region must tolerate periods of immersion in seawater, followed by periods of exposure to air. Some creatures cling to rocks to avoid being swept away by waves. Others burrow into sand or mud to survive the changing conditions. Seaweeds and algae have evolved flexible structures that allow them to endure both underwater currents and drying air. Although these modern ecosystems evolved long after the origin of life, they demonstrate how tidal environments encourage biological diversity and resilience. The constant alternation between wet and dry conditions, along with changes in temperature, salinity, and sunlight, creates a wide range of microenvironments where different chemical and biological processes can occur. If early life did begin in tidal environments, it would have developed in a setting already rich in environmental variation. Over time, primitive self-replicating molecules might have adapted to these changing conditions, eventually forming the first simple cellular organisms. It is important to remember that scientists are still investigating many possible scenarios for the origin of life. The tidal pool hypothesis is only one of several ideas currently being explored, yet it highlights an intriguing connection between planetary physics and biology. The tides themselves are driven by gravitational interactions between Earth, the Moon, and the Sun. Those interactions shape the movement of oceans across the planet's surface. If tidal cycles helped create the environments where early chemistry evolved toward life, then the gravitational partnership between Earth and the Moon may have influenced not only the oceans, but also the earliest steps in the development of living systems. In that sense, the quiet rise and fall of the tides might represent more than a simple movement of water. They may also echo a much older process, one that helped prepare the conditions in which life itself first emerged on this remarkable planet. The tides we experience on Earth may feel gentle and familiar. They raise the sea along coastlines, move quietly through ocean basins, and reshape shorelines over time. Compared with the dramatic forces that shape stars or galaxies, Earth's tides seem almost modest, yet the same gravitational process responsible for our tides operates throughout the universe. In other parts of the solar system, tidal forces can become so powerful that they reshape entire worlds. One of the most striking examples can be found among the moons of Jupiter. Jupiter is the largest planet in our solar system, containing more mass than all the other planets combined. Its powerful gravity governs a complex system of moons that orbit around it in intricate patterns. Among these moons is Io, a world that appears at first glance to be similar in size to our own moon. Io has a diameter of about 3,600 kilometers and is composed largely of rock, but its surface looks nothing like the quiet grey plains of Earth's moon. Io is the most volcanically active body in the entire solar system. Hundreds of volcanoes cover its surface, some erupting with plumes that rise hundreds of kilometers above the moon. Lava flows spread across its landscape, creating vivid patterns of red, yellow, and black deposits. For many years, scientists wondered what could power such extraordinary geological activity on a relatively small world. The answer lies in tidal forces. The role of tides in shaping Io's interior was explored by planetary scientist Stan Peale during the 1970s. Peale and his colleagues examined the orbital interactions between Io, Jupiter, and two neighbouring moons named Europa and Ganymede. Their calculations revealed that Io experiences intense gravitational stretching as it moves along its orbit. Unlike Earth's moon, which follows a nearly circular orbit around Earth, Io's orbit is slightly elliptical. This means its distance from Jupiter changes slightly during each orbit. As Io moves closer to Jupiter, the planet's immense gravity pulls more strongly on it. When Io moves slightly farther away, that pull weakens. This continual variation in gravitational force causes Io to flex repeatedly. Imagine squeezing and releasing a soft rubber ball over and over again. The ball deforms slightly each time pressure is applied. If this process continues long enough, the material inside the ball begins to heat up. Something similar happens inside Io. The constant stretching and relaxing of its interior generates friction within its rocks. That friction converts mechanical energy into heat, a process known as tidal heating. Over time, this heating becomes strong enough to melt portions of Io's interior rock, producing vast reservoirs of magma beneath the surface. When that molten material erupts through volcanoes, it reshapes the moon's surface in spectacular ways. Io demonstrates how powerful tidal forces can become when a moon orbits very close to a massive planet. But tidal heating is not limited to volcanic worlds. Other moons in the outer solar system experience tidal forces that create very different environments. One of these worlds is Europa, another moon of Jupiter. Europa is slightly smaller than Earth's moon and is covered by a thick shell of ice. At first glance it appears cold and lifeless, with a bright surface crisscrossed by long fractures and ridges. However, beneath that icy crust, scientists believe there may be a vast ocean of liquid water. Evidence from spacecraft missions, such as NASA's Galileo spacecraft, suggests that Europa's icy shell floats above a global ocean that could be many kilometers deep. The energy required to keep this ocean from freezing solid may come from tidal heating. As Europa orbits Jupiter, it experiences gravitational forces similar to those affecting Io, though less intense. These forces flex the moon's interior slightly, generating heat that may help maintain liquid water beneath the surface ice. Another fascinating example lies far beyond Jupiter in the realm of Saturn. One of Saturn's moons, named Enceladus, is a small icy world only about 500 kilometers in diameter. Despite its modest size, Enceladus has captured enormous scientific interest. Spacecraft observations by NASA's Cassini mission revealed towering geysers of water vapor erupting from fractures near the moon's south pole. These geysers spray particles of water ice and vapor hundreds of kilometers into space. Analysis of these plumes indicates that they originate from a subsurface ocean hidden beneath Enceladus's icy crust. Once again, tidal heating appears to play a crucial role. As Enceladus orbits Saturn, gravitational interactions with the giant planet and nearby moons flex its interior. This flexing generates heat that keeps portions of the subsurface ocean in a liquid state. In these distant environments, tidal forces are doing something remarkable. They are creating pockets of warmth and liquid water in places that would otherwise be frozen solid. Liquid water is considered one of the key ingredients for life as we know it. For this reason, moons such as Europa and Enceladus have become major targets in the search for extraterrestrial life. Scientists are now planning future missions to study these worlds more closely and investigate whether their hidden oceans might contain the chemical conditions necessary for living organisms. All of this research connects back to a simple idea. Tidal forces are not merely a curiosity affecting Earth's oceans. They are a universal physical process that can shape the internal structure and evolution of celestial bodies. On Earth, tidal forces raise the oceans by a few meters. On Io, they generate enough heat to power hundreds of volcanoes. On Europa and Enceladus, they may sustain oceans hidden beneath layers of ice. The same gravitational physics operates in each case. By studying tides on Earth, scientists gain insight into the fundamental mechanics of tidal forces. These insights help researchers interpret observations of distant moons and planets. In this way, the quiet motion of the tides along our own coastlines becomes part of a much larger scientific story. The rise and fall of Earth's oceans reflect the same cosmic principles that shape volcanic moons, hidden oceans, and perhaps even environments capable of supporting life elsewhere in the universe. Tides remind us that the gravitational relationships between celestial bodies can influence worlds in profound ways. From the gentle breathing of Earth's oceans to the fiery eruptions of distant moons, tidal forces continue to shape the landscapes of our solar system. When we watch the tides rise and fall along a shoreline, the motion can feel timeless. The ocean comes in, the ocean goes out, and the cycle repeats with quiet reliability. It is easy to imagine that this rhythm will continue forever in exactly the same way. But the gravitational partnership between Earth and the Moon is slowly evolving. The tides that shape our coastlines today are part of a much longer story that stretches across billions of years into both the past and the future. To understand how this system changes over time, scientists study the long-term dynamics of planetary motion. One researcher who has made important contributions to this field is the French planetary dynamicist Jacques Lascar. Jacques Lascar has spent decades studying the stability of planetary orbits and the long-term evolution of celestial systems. Using powerful computer simulations and advanced mathematical models, his research examines how the gravitational interactions between planets and moons unfold over millions and even billions of years. These calculations reveal that the Earth-Moon relationship is not static. Instead, it is gradually changing due to the same tidal interactions that move the oceans each day. One of the most important effects of the Moon's presence involves the tilt of Earth's axis. Earth does not spin perfectly upright relative to its orbit around the Sun. Instead, its axis is tilted by about 23.5 degrees. This axial tilt is responsible for the changing seasons. As Earth travels around the Sun, different parts of the planet receive varying amounts of sunlight throughout the year. The stability of this tilt turns out to be crucial for maintaining a relatively stable climate over long periods of time. Without the Moon, Earth's axial tilt might vary dramatically. Gravitational interactions with other planets, particularly Jupiter, could cause the tilt to wander chaotically over millions of years. Computer models suggest that a moonless Earth might experience shifts in axial tilt, ranging from near 0 degrees to more than 60 degrees. Such extreme changes would dramatically alter the distribution of sunlight across the planet. Polar regions could receive intense sunlight at certain times, while equatorial regions might experience long periods of darkness. The climate would become far less predictable. The presence of the moon helps stabilize Earth's rotation. Because the moon is relatively large and close, its gravitational pull exerts a steady influence on Earth's spinning motion. This stabilizing effect keeps the axial tilt within a relatively narrow range over long periods of time. As a result, the seasonal patterns we experience today have remained broadly consistent for millions of years. The same gravitational interaction that stabilizes Earth's tilt also continues to shape the orbit of the moon itself. As discussed earlier, tidal friction transfers energy from Earth's rotation into the moon's orbital motion. This transfer gradually pushes the moon farther away from Earth. Modern measurements using laser ranging experiments show that the moon is currently receding at a rate of roughly 3.8 centimeters per year. That rate is extremely small when considered over a human lifetime. Over geological timescales, however, the effect becomes significant. Hundreds of millions of years ago, the moon was noticeably closer to Earth than it is today. During that time, tidal forces would have been stronger, and tides along ancient coastlines would likely have been more extreme. Looking far into the future, this gradual separation will continue. As the moon drifts farther away, its gravitational influence on Earth's oceans will slowly weaken. The tidal bulges it produces will become slightly smaller, and the strength of the tides will gradually decrease. At the same time, Earth's rotation will continue to slow as tidal friction removes energy from the system. Over billions of years, these processes could lead toward a state known as tidal locking between Earth and the moon. In such a configuration, Earth's rotation period would eventually match the moon's orbital period. The same side of Earth would always face the moon, just as the same side of the moon always faces Earth today. If that situation ever occurred, the tidal cycle would look very different from the one we experience now. However, this scenario lies extremely far in the future, well beyond the expected lifetime of the Sun as a stable star. Long before such a final state could be reached, changes in the Sun's evolution will dramatically alter conditions within the solar system. For the foreseeable future, the Earth-Moon system will continue its slow and graceful evolution. The Moon will inch outward along its orbit. Earth's rotation will lengthen by tiny fractions of a second over millions of years. The oceans will continue to respond to the shifting gravitational relationship between the two bodies. Throughout all of this, the tides will remain a visible expression of that connection. Each rising tide reflects the gravitational pull of the Moon stretching Earth's oceans. Each falling tide marks the moment when coastlines rotate away from those regions of elevated water. The process unfolds continuously, linking the motion of the sea to the motion of celestial bodies across space. In this way, the tides represent more than a coastal phenomenon. They are evidence of an ongoing gravitational relationship between two worlds. The Moon circles Earth. Earth spins beneath the oceans. Gravity binds the two together in a partnership that has lasted for billions of years and will continue far into the future. And every time the tide rises along a shoreline, it quietly reminds us that the oceans of Earth remain connected to the silent motion of the Moon above.